Today we're going to go through a crash course of acids and bases. In this video, I'm going to use the Bronsted-Lowry definitions where the acid donates a proton and the base accepts a proton. The pH is equal to the negative log of the concentration of the hydrogen ion, which is the protons, or it can also be seen as the H3O plus ion concentration, which is hydronium. These two mean the same thing. pOH is the opposite, which is the negative log of the hydroxide ion, OH minus. But if you're given the pH and you're looking for the hydronium and hydroxide concentrations, you just do 10 to the negative pH or 10 to the negative pOH to find whatever you're looking for. Another important thing to know is Ka and Kb. These are the dissociation constants, which means that they tell you to what extent the acid or base splits up into its ions. So pKa and Ka have the same relationship as pH and H3O plus concentration. So pKa is the negative log of the Ka, and pKb is the negative log of the Kb. And then to find Ka and Kb from pKa and pKb, you just do 10 to the negative pKa or 10 to the negative pKb. The dissociation constants Ka and Kb are usually very obscure in small numbers, so they're usually given in a problem, or you'll have to find it from a pKa or pKb. And you use that Ka or Kb value to find the concentration of the hydronium or hydroxide, which can then give you a pH or pOH, whatever you're looking for. Now I'll do one example problem that applies some of these concepts. To find the pH of a 0.1 molar sodium chloride solution, you need to make an ice table. First, write the net ionic equation. H2O isn't in the ice table because it's a liquid. I just fill out our ice table with our known concentration values, and we're looking for X to find the OH minus concentration, which can give us a pOH and then give us pH. Since we were given the base, which was the chloride ion, then we have to find the X using Kb. However, we currently have Ka, so we have to find the Kb value from the Ka. And this you should memorize. Ka times Kb equals Kw, which is 10 to the negative 14th at 25 degrees Celsius. Given that, we know that Kb equals 10 to the negative 14th divided by the Ka, which is 1.1 times 10 to the negative second. Plugging that into the calculator, you get Kb equals 9.1 times 10 to the negative 13th. Now we can use the Kb to solve for X, and these are more formulas that you should know. Kb is equal to the concentration of the conjugate acid times the concentration of hydroxide over the concentration of the base. Similarly, the Ka expression, which is used for acids, is the concentration of the conjugate base times the hydronium ion concentration over the acid concentration. Remember that for these K expressions, it's always products over reactants and the ions on top and the given base or acid on the bottom. And in this example, we're going to use Kb because we're given a base. I plugged in the equilibrium concentrations for each value from our ice table, and then I used the Kb that we calculated earlier. So now all we have to do is simplify and solve for X. Now we'll use a shortcut here. So in most cases where you have Kb or Ka as a really small number, the X right here can actually be neglected because when you multiply it over to solve for the X on this side, then you end up multiplying it by such a small number that it's basically insignificant. With that being said, you multiply the 0.1 over to the left side to get 9.1 times 10 to the negative 14th equals X squared, and finally square root both sides to get X equals 3.0 times 10 to the negative 7th. Now that we found the X, you have to make sure that you know what X is. So our ice table tells us that OH minus is equal to the X, so that means this is the concentration of hydroxide ions. But that's not what we're looking for because we're looking for pH, so we have to change the concentration of OH into pOH and then finally to pH. So you take the negative log of the hydroxide ion concentration times 10 to the negative 7th, plug that into the calculator and you get 6.52. And since this is a pOH, we need to find the pH by subtracting that from 14, which is the total, and we get 7.48 as our final pH value. And that's how you go from given molarity and Ka or Kb value of an acid or base to finally finding the pH or pOH that you're being asked to find. I hope this video was helpful, and I tried incorporating as many concepts I could into this one example problem so that you can apply this to lots of other acids and bases questions that you come across. Good luck!